Good morning and welcome to lecture 27 of Quantum Physics for Non-Physicists. And today we will talk more about spin, and we'll generalize this concept of spin that we had in qubits, and you'll see how it can apply to many things. And then later on we'll use this to derive the physics of the simplest atom that there is, so the Eigen atom. And for this we'll follow chapter 12 of the book, of the Schumacher and Westmoreland book, very closely. Okay. And our daily analogy is with floppy disks. So floppy disks were used maybe in the 80s, early 90s, but nobody has used a floppy disk in a very, very long time. However, we still use the symbol of the floppy disk as the safe symbol, right? So there was this kind of transference of meaning from like the actual physical implementation of the function of saving something to just this having this concept of this functionality of save, right? And it's going to be the same thing with this concept of spin. So we'll see that we're going to have very similar functionality applied to many different systems. So for example, we saw that for a qubit we had this Pauli operators that satisfied some commutation relations. And then we'll see that for n-dimensional systems, we'll find very similar commutation relations. And even for infinite dimension systems, like continuous systems, we'll find, again, some operators that satisfy the same relation. So they have all kind of the same functionality. They will behave in similar ways, just like you can save things on many different kinds of programs, right? The actual implementation doesn't matter as much as what the function is meant to be. Okay, so it's going to be the same thing. We'll find the same concept popping up and up again, and we'll try to find a way to formalize what they all have in common. Okay, good. So let's just see where we are in the great scheme of things. So we've done everything up to now except this notion of entropy, which we will not dwell into, but you'll see it, for example, in the mock exam, but don't worry about it. But the big thing that was missing from this whole scheme was now talking about spin and rotation. So we'll talk about generalized spin, what are these ladder operators, what does it mean to add spins, etc. And then we'll see how to apply this to a 3D problem, namely the orbital angular momentum of a particle. And then we'll use this to solve the hydrogen atom. Okay, and yeah. There's one thing that you'll do only in this tutorial this week, which is the harmonic oscillator. That's one example of having a spin with dimension n. Okay. So what did we mean by spin, right? I've been dropping this word now and then, but I've not really defined it. So we started with this abstract qubit idea and have this Pauli matrices there. Yep. And they had some properties. So for example, they were all Hermitian. And every time, if you square them, so you apply them and then the same matrix again, then you get the identity. Because they corresponded, if you remember, to kind of a rotation around the Bloch sphere, but such that if you apply it twice, you go back to where you were to start off. And more important, they satisfy these commutation relations. Okay. If you don't remember how to derive this, you can simply do it by hand by just multiplying these matrices and subtracting. Okay, so the main idea is that whenever you have the commutator of two matrices, you get the other one with some factor. Okay, which in this case was just I. So then we saw, when we first talked about the Schrödinger equation, we saw an example of applying this to an actual physical system, where that was something like, we just said, oh, it's like the spin of an electron. So it's an internal property of a particle. And then the matrices that we considered were exactly the same as the Pauli matrices, just with this factor h bar that gave it the right units for measuring something. Okay, so well, this is the spin of the electron, that's this internal property of the electron. And one way to measure it was this Stern-Gerlach experiment, where we sent the electron through a magnetic field that coupled kind of this internal spin, this internal qubit, to the position degree of freedom, or to the, momentum degree of freedom, so that then we could see that if the spin was up, the particle would end up here, and if the spin was down, it would end up down there. So this was a way of measuring it. And by the fact that you'd only get 2 blobs here, you find out that the spin can only have 2 values. Okay. And the main thing is that they had the same kind of relation. And where else does this kind of spin show up? Well, it shows up a lot. For example, when we consider individual atoms, we'll see this next time. That, if you look at the energy levels of the atom, an atom is essentially like a bunch of protons and neutrons that are kind of stuck in the center. And we think of this, like the solar system. Of course, we know that the sun is moving through the galaxy, but for practical purposes, because the sun is so much larger than the objects around it, we can consider the sun to be fixed, and we can compute like the orbits of the planets around it. It's a very loose analogy, but the idea is when we'll solve the hydrogen atom, we'll think of the nucleus as being like in a fixed position, and then we just consider the particle electron as being our free particle going around it. Okay, and then these particles, they can be at different energy levels, and it will depend on something called the orbits that we'll see, like, so they can be farther away from the nucleus or closer. But the other degree of freedom that matters a lot is going to be the spin, whether the spin is up or down. And sometimes this leads to like a little difference of energy between spin up and down. It always depends on, I don't know, whether this is in the magnetic field or not, for example. Okay, the other example where it appears a lot is when you study magnetism. So what do I mean by this? Of course, we will not go into detail in this course. If you want to learn more, you can take, for example, statistical physics or solid state physics, or even superconductivity, any course that has to do with magnetism. We'll talk about this. But essentially, the idea is that you have, in a metal, for example, all your atoms are kind of very neatly arranged in a grid. So for example, this kind of square grid. Okay, so everywhere there's an atom. And then the only things that are kind of free are the electrons that are around these atoms. Okay, so let's consider only one free electron per atom. And then the total Hamiltonian of the system, of course, it has the ground energy of the atoms, but the only thing that can change will be something, for example, so look at this term here. This term is the sum over all spins, so all i's, of some constant times, for example, the spin in the x direction or in the z direction, etc. Tensor the identity and the rest. So this corresponds to there being a magnetic field in one direction, so either in the x or z direction, like physical z and x. And this tells us that the spins kind of like to be aligned with the magnetic field or against it, depending on the sign of this thing, right? So remember that this system will tend to go to a thermal state. At low temperature, this means that it wants to go closer to the ground state. And the ground state is just the state of the least energy of this, right? So if you have this case here, if you only have this term, then this means, well, I want, if these HIs are positive, then I want all of this to be, all of this to have, well, if they can only have spin plus or minus H bar, then I want this to have as close as possible to like being all aligned in the same direction. Okay. All right. Then you can also have, for example, interactions between two spins, between two neighbors. So it's like this electron can feel this electron nearby, and we can model this by saying, for example, well, it's a factor times the product of the two spins of this electron up and this electron down. Okay. So for example, if this is a positive number and they are, and these two electrons are both have spin up, then this will be a positive number. So they don't like this. So they want to have, they want this to, so they would want this to be anti-parallel. So one goes up and the other one goes down, then you get a negative number here. So this term would have kind of lower energy overall. right? But because there's a minus sign here, it's the other way around. So it's like this kind of Hamiltonian, which, by the way, this is the only sensible Hamiltonian that has some physical meaning that we can solve analytically. So whenever we start getting a bit more complicated, so for example, we could have interactions between 3 spins, or you could have terms that just look a bit more complex than this. Whenever it gets a little bit more complicated, you cannot solve it analytically. You need to throw numerics at it. You need to run simulations, etc. But for this model, the Ising model, we can solve analytically. And what you get is that, so if this constant is positive, because there's a minus sign here, the spins want to be aligned. So they want this number to be positive, right? So that overall, this is negative. Remember, you want to go as low as possible in your energy. So spins want to be aligned, so you end up with a material that looks mostly like this. Okay, and that's what a ferromagnet is. And there's something that responds well, for example, to magnets, that goes to magnets. If these terms are negative, sorry, then they want to be anti-parallel, so you get a system where it's like up, down, down, up, and so on. And that's an anti-ferromagnet. It's a different kind of material with different properties, like different magnetic properties, for example. And you can do a lot, and the only physics you need really is just this physics of the spin. So you can learn all the properties of the system, like also, for example, you can say, oh, if I shoot a spin here in a certain state, how long does it take until that state reaches some other part of the lattice, for example? You can learn all the properties of such materials, very complex materials, just by studying spins, right? Just by studying this kind of very simple Hamiltonian. And in fact, all of solid state physics is looking into this kind of systems, this kind of Hamiltonian. So that's why spin is important. On the other hand, there are systems that have similar properties to spin, but they're not quite the same as we saw now. So one is that there are larger particles. I will not get into details now, but there's larger particles in which you can do this Stern-Gerlach experiment. So you put it in contact with a magnetic field for a small amount of time. You know that it will couple spin to the momentum, and then you measure what happens at the end. And instead of 2 blobs, sometimes you end up with 3 blobs, okay? Or with 5 blobs. So in a way, you have some property inside here that kind of acts like spin in the same way in the experiment, but it's not exactly the same because, with the spin that we know and love, you only had 2 blobs, and now here you have 3 possible eigenvalues. Another thing that is a bit similar, we don't fully see the connection yet, is rotations in 3 dimensions. Okay? And the idea here is that rotations along different axes do not commute. So for example, if I take a book, okay, and you're looking at this side of the book, and I turn it first around the x-axis and then around the z-axis, okay, then you end up with the butt of the book. But if I turn it first around the z-axis and then around the x-axis, you end up looking at a different part of the book, right? So it's not the same to do things in one order or in another order. And in fact, the operation that connects this to this one that we saw before, it's a rotation along the y-axis. So much like, much like this idea. Right, it's when it commutes 2 rotations, you get the other rotation somehow. Okay. So, but we don't know yet what else it has in common with spin, but this is something that we'll formalize in this lecture, in the next lecture. The other thing that you'll see in the tutorial is systems called harmonic oscillators. And these are kind of the quantum generalization of something as simple as having an object attached to a spring, and then you can pull the object and it will oscillate. And if you map like x of t, then it will look like something like this, right? And this thing some people joke then that making physics is just solving the harmonic oscillator problem into more and more and more detail, because it has lots of fun properties. And as it turns out, a similar thing happens, for example, in systems like trapped ions, which are used for quantum computing, where the idea is that you have some magnetic fields, blah, 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 it doesn't matter, where you put some ions, which are like atoms with one extra or one fewer electron. So you put this kind of atoms, the ions, trapped in a region, and if you look just at the position degree of freedom, it actually looks very much like a harmonic oscillator. And meaning that the kind of the effective Hamiltonian for this degree of freedom looks a lot like the Hamiltonian for the classical system. You'll see an example of this in the tutorials. And in this case, if you map the eigenvalues of the Hamiltonian, they look exactly like this ladder system that we saw for the energy battery when we talked about thermodynamics. And we'll see that here, we can also look at this as kind of a spin system where this is like the Z direction and X direction is kind of going up and down this ladder. We'll see this. So what we'll do today is kind of formalize the connections between all of these kind of systems by just thinking about spin in a more abstract way. So I'll write what the roadmap is going to be, because it's very mathematical, but it's a nice kind of maths. It's not the kind of maths where we're just cranking up something, right, to get the results. Like, oh, we know that we need to do decomposition, and now let's get the results out. But it's, in fact, the kind of maths where we're discovering something as we do the maths. So what we'll do is we'll start with these commutation relations for the normal spin, and then we'll generalize them to larger dimensions. Okay. So instead of dimension 2, this was essentially a qubit, then we'll take something of dimension n that is unknown. And in these larger dimensions, we'll define some other operators, and they will help us find some properties of the Hilbert space, also some properties of how the Eigen States of, for example, of SZ look like, etc. Okay, this we will all do today. And then we will see some examples of this. So one example will be these bosons, the other example will be the harmonic oscillator. This we'll do in the tutorial. Then we'll see the continuous case where we'll get angular momentum instead of discrete spin. And then in order to look at, what the eigenstates of this spin operators in angular momentum case will be, we'll need to look again into 3D and how to change coordinates in 3D. And then we'll see what these eigenstates are, and they'll be precisely the eigenstates that will help us solve the hydrogen atom. Okay, so this part will for sure be on Thursday, maybe a little bit of this as well. We'll see how it goes. Very good. So let's start. This was all just motivation up to now. And now we get to start. So we'll take some Hilbert space H of dimension n, which is unknown for now. Okay, we don't worry about this for now. And we'll just say, well, there are some operators here. I can build some operators that have these properties. I know nothing about, I know that this matrix should be as large as n, but I know nothing about their eigenstates or eigenvalues for now. Okay. But I can determine this by force. So I just choose one of them to be kind of the computational basis, like we had, like we had the Z basis be the computational basis in the case of qubits. Here we can choose the same. So we just say we define kind of Z to be the standard basis. And what I mean by this is we just say, well, let's look at the eigenstates of Sz, okay? And let's just say, well, Sz applied on some state, it will have some eigenstates, right? And the eigenvalue, well, for sure, because we have this h here in the commutation relations, it will have units of h, and then it will be some number that we don't know yet, okay? And so this is still unknown. Could be anything, could be any complex number, sorry, any real number, because it will turn out to be Hermitian, but you know, these things will turn out to be kind of integers. Doesn't matter. For now, it could be anything. And now we'll say, okay, so then we can just label these eigenstates by m. Just call them psi m, but let's not write psi all the time, so we just call them m. And you know, for now we don't know, but these states could be degenerate. So this operator could be such that it has many eigenstates with the same eigenvalue, right? We don't know. So because we don't know, we can say, well, there's some other property of this state. Let's just call it alpha, which maybe can be distinguished by the other operators, or by some other operator at all in my big Hilbert space, but cannot be distinguished by this one. Okay, so this can be anything. So this could be and if I draw a picture of what these eigenstates are, so this would be kind of the value of Sz, and we can draw them kind of like this. So this could be m alpha. Here's another one with m alpha dagger, and then at some point there will be some m prime. Okay. So there's this kind of direction where there's just different alphas that we don't know, and this direction up here, which is what this operator can distinguish. And in principle, there could be many such states, and we don't know yet. You know, it could even have different states for different values of m, for example. We don't know yet. Okay. But now we're going to define a new operator, which will help us a bit. So define new operator S square. And S square we just define as being the sum of the squares of all the others. And for now, we don't know yet why we're doing this, but I know that in retrospect, this is going to be useful. So let me get, where is he? Let me get Sherlock here. If you remember, this is our symbol for something that we define because we know the solution. Okay, so I know that this will be useful later. That's why I'm defining it. Okay, so just hang on with me for a second. So I define this new operator. And so the first thing we do, because all we know about this operator is their commutation relations. So we're going to look at the commutation relation between S squared and, for example, Sz. Well, we just do the sum. Sz plus Sy squared Sz plus Sz squared Sz. Now, this term we know is 0 because it's the same operator. Of course, it commutes with itself. And for these other terms, we have to remember this rule that when you have the commutator between A, B, and C, this was A, the commutator between B and C. plus the commutator between A and C times B. So we just have to remember this rule. And then we can solve this. So what we get Sx, Sz plus Sx, Sz, Sx plus Sy, Sz plus Sy, Sy. Okay, and now we just insert here the commutation relations that we know. Let me just get them again. Let's go get them. Okay. So what is this? This is going to be IH bar. And now what? So Sx. And now Sx time commutated with Sz is minus this. Right. Oh, I missed an H bar somewhere. And everywhere else before it. Oop. That's embarrassing. Where else is it? H bar. Yeah, that's it. Okay. Good, so then it's minus that. So Sy. And now we get minus Sy, Sx. And now the two terms from out here is Sy. And now this commutator is exactly this. So you get Sx, Sx plus Sx, Sy. Okay. And now they kind of cancel each other, right? So it's 0. And if you want to solve it, you can see that exactly by the same maths, you'll get that this is also the commutation relation between S2 Sx and S2 and xy. Yeah, so they're exactly the same. Good. So what does this tell us? It tells us that this new operator, S square, it commutes with all of our spin operators, so they share an eigenbasis. Okay. So now we will consider only the subspace with a particular eigenstate of S squared. So, and the reason for this is, again, because we know that this will give us good things. So I will consider just the subspace of the Hilbert space, which I called HS. And HS is just a span of all the states that have the same that are going to have the same eigenvalue for this S square operator. And so what's the eigenvalue going to be? Well, because it's square, I know it's going to have like H square somewhere. So I'm going to put here H square, and then it's going to be a number. Okay, so it's going to be some number that, I mean, ideally depends on this S that I'm trying to define. So we would choose the number that makes the most sense. And here I'm going to use my Sherlock, meaning that I know in the end what result I want, so I know what number I want to put here. And you could think, oh, maybe it's S squared, but as it will turn out, the one that's most convenient for later maths is going to be S plus 1. Okay. And for now, it's like, why this? You'll see later why this. Okay. But again, this could be anything for now. Right. Anything in R. All I know is that this is a real number, and that, of course, I can write any real number as this if S is also a real number. Okay. As it will turn out, it will be a very convenient one. Okay, so I'm going to define a few more operators. So now I'll define what are called the ladder operators. S plus and S minus. And these will turn out to be very important. So what are they? And we will see why they have these names very soon. So this is Sx plus I Sy, and S minus is going to be Sx minus I Sy. Note that if Sy and X are Hermitian matrices, then this means that S plus dagger. What is this? Well, this is Sx dagger minus I Sy dagger. And if those two are Hermitian, then this is just Sx minus I Sy S minus. Okay. So they are the transpose conjugate of each other. Similarly, S minus is going to be S minus dagger is going to be S plus. Okay. All right. So what we do, the only thing we've got is commutation relations. So we're going to work with them, and then we're going to see something cool happen. So we define these things. Oh. Put them in a box. So commutation relations. So let's see what's the commutation between SS and N plus. Okay, so we know this. It's just going to be SZ and X plus I S Z and SY. Well, this one is IH bar SY, the first term, plus I, and here is minus I H bar SX. Okay, where again I just use this commutation relations. So this is minus that. So I get a minus sign there. Okay. But what is this? Well, this is H bar times ISI and I plus SX, right? Because I times minus I is 1. But that's H bar times S plus. And that's an interesting commutation relation, because look at this. So what happens if I apply then S Z S plus to one of my eigenstates of Z? Well, then I know that this is S plus SZ plus the commutator, right? By definition of the commutator, times the same state. Okay, but that's just S plus times SZ plus H bar, and now comes the state. But I know what applying SZ to the state does, right? Because it's an eigenstate. I should just get this out. Okay. So then I have S plus, and then I have MH bar plus H bar, and my state. I'm going to have to make this a little bit smaller so that everything fits. Okay, so this is what? So this is H bar times M plus 1 S plus and alpha. Now, if I put some brackets here, okay, and I call this state, for example, state psi, then what I got is that this state psi is an eigenstate of SZ, right? With this eigenvalue M plus 1 times H bar. So I'll write again here that this is now the new eigenvalue. And this is an eigenstate. So what did I get? I get that the action of acting with this operator on this state somehow gives me an eigenstate of the eigenvalue kind of above it. Okay. So let me write this. So the conclusion is that if I apply with S plus on alpha, what I got was an eigenstate for the next value of the value M plus 1. And I don't know what else happened, right? They could have changed this alpha here, I don't know. And again, like, I mean, there might have been some kind of normalization that needs to be done. So maybe it added a phase or something, I don't know. But it cannot be determined by this. So back to our picture. Let's get our picture of the eigenstates. All that I know for now is that this S plus takes us from there to there. Okay, maybe it does this, maybe it does that, we don't know. But it takes us from kind of this space of eigenvectors with the eigenvalue M to the M plus 1. Okay, so let's put here M. M plus 1 alpha. And then if we applied it again, you know, maybe it would take us to M plus 2. Okay. Fine. Okay, so that's why we call this one the raising operator. Similarly, we can do the same for the minus operator. So I will not do all the maths here, but you can try at home. So if you do set S minus, then you get minus H bar S minus, which tells us that if you apply SZ to the state S minus M alpha, then you end up with M minus 1 H bar, and then the same state M alpha. Okay. Which again tells us that S minus applied to this state. You know, it's some kind of constant that we don't know yet. And the state below it. So we call this the lowering operator. And if we look at this picture, then it means that the S minus will map us like this. From one eigenspace to the one below it. And again, we don't know if it goes like this or if it goes like that. We don't know what's happening in this alpha parameter. Okay. So this is why we call them, this is why we started by calling them ladder operators. So because they really just go up and down like a ladder. Okay. And in the case of qubits, where there's only two states, right, that we saw, then really the going up just corresponds to this, and the one that goes down just corresponds to this thing. They are very similar to the ones that we saw when we talked about thermal engines. Okay, you will do this in the tutorial. We'll do these examples in the tutorial. All right, so maybe this is a good place to have a break. So what we have for now, let's just see. So we have some dimension n that we don't know. We label the states in this subspace, in this Hilbert space, by the eigenvalue on the z direction, on the z operator, plus something that we don't know. These eigenvalues are mh bar. Then we define this big operator as squared, which is just the square of all the others, of all these matrices. We saw that it commutes with all of these matrices, and we took the subspace that is just s plus one eigenvalue for this thing, okay, which will become relevant in a bit why we took this one. Then we defined these ladder operators, and we saw that we can use them to go kind of up and down these Eigen States, okay, in the z direction. So let's take a break here, and let's continue at 11:45. Okay. All right. So we have this kind of picture of what the Hilbert space looks like in terms of how the SZ sees it. Okay, and what we'll do now is kind of see first what happens in this direction. We'll see that you cannot keep going up forever, you have to stop, and you also cannot keep going down forever, you'll have to stop there. And then you'll see what happens in this direction, and you'll see that actually you cannot have different number of states for different eigenvalues of SZ, so that if you have 3 states here, you must also have 3 states there and 3 states there. Okay, so in the end, we'll see that this picture is less free than we thought. It's really kind of a rectangle. Okay. And again, we're not doing this for fun, although it is fun. We're doing this because it has incredibly many applications, like all these things we saw in the beginning of the lecture. Okay, so first let's bound word space vertically. And the trick that we're going to use, well, is that the inner product, by definition, if you do the inner product of a state with itself, even if it's not normalized, this must be always positive. So in particular, if I take psi to be my S plus applied to some state, to some eigenstate of Z, then what do I get? Well, M alpha, S plus dagger, S plus alpha. This must all be larger than 0. But we saw that S plus dagger, this is just S minus. And this whole thing needs to be larger than 0, so let's just see what S minus S plus is. So that's Sx minus I Sy Sx plus I Sy. Okay, so we have 4 terms. The first 2 terms are S squared plus Sy squared. And then we have this with this. So plus I. Now Sx Sy minus Sy Sx. Right. Well, with this, we know that this is the commutator between Sx and Sy, so that's plus I H bar I Sz. Right? And what we know of this part here, well, this thing is the same as S squared minus Sz squared, right? Remember, we define S squared as being the sum of the squares of all these spin operators. So S squared is this plus this plus this. If you only have those two, get that. Okay, so what we have over here, we have S squared minus Sz squared plus, no, minus. Yeah, that's right, minus. So minus H bar. Okay. Now we can plug this back in here. So let's just write it in a different way. So S squared minus Sz, and here is sorry, Sz plus H bar. Okay, there we go. Good. So now we plug this in here again. So we have that 0 is smaller than M alpha, and now this whole thing, so S squared minus Sz plus H bar M alpha. Okay. And what is this? M alpha. And now I can just act with these operators on this state. Yeah. So first we get S squared minus Sz, and here we have M H bar plus H bar, right? M alpha, because it's an eigenstate of Sz. And now we can act with the other two. So first of all, if I act with S squared, we decided before that this is S plus 1 H bar square. And here minus, we get M H bar. So let's put H bar square here, M plus 1 M alpha. Okay, now what's in the middle is a number. And then we have the inner product of this state with itself, which was normalized to start with. Okay, so that then we have just that H bar square times S plus 1 minus M plus 1. This thing must be larger than 0, right? That's what we started with here. Okay, the H bar square we don't care about because it's a positive constant. But what this tells us is that if we send this term to the other side, then the only way for this to be positive is if S is always larger than M. Okay, so the conclusion is for this to be positive, S is larger than M. Okay. We can do now the other way around. So if we did now, sorry. If we did this, with instead of S plus, just taking here the S minus, okay, then we do exactly the same calculation and we end up with a solution that S must also be larger than minus M. Yeah. Okay. So we have done that. The overall conclusion is that S is always larger than the absolute value of M. The absolute value of M. Okay. So let's suppose that our M goes like this. Okay. Maybe our first M is, I don't know, 0.7. Okay. We'll start with some arbitrary number and then we'll see. We know that if we apply S plus, we'll end up with 1.7. If we apply again, we'll end up with 2.7, etc. But at some point, we're going to hit S. Okay, suppose that S is now, I don't know, 5. Okay, at some point, you're going to hit S, which means that when we apply again this S plus operator, we cannot get a valid state because, if it was a state with an M equals this plus 1, then we would not satisfy this condition. So what's the only solution for this? Well, the only solution, remember that we said that when we apply the state S plus, there's some kind of constant times this state. And this constant can in particular be 0. Okay, so the only kind of mathematical solution to this problem is that if we apply S plus to M max alpha, then we get 0. In the same way, if we apply S minus to some N minim alpha, then we'll get 0. Okay. All right. And now, in principle, that could be like a little gap here, right? So this could be 4.7 and S be 5. But that's not the case. Okay. And so what this fixes is that, well, we have to reach 5 exactly. If we apply it again, then we get the null vector, and here we have to reach minus 5 exactly. So this means that this picture here is not complete. So we'd have to start with the maximum M equals 5, 4, 3, 2, 1, 0, until minus 5. Because otherwise we jump this. So M max is S, and this is minus S. All right. Okay. So M can belong to minus S plus 1, tuka, S minus 1, S. These are the allowed values for M. Well, which means what? For now, we thought that S could be any number. So I said 5, but it could be any real number. But now we know that, I mean, we can only go in an integer number of steps, right? We cannot go like half a step. So the difference between S and minus S must be an integer number, so that we have an integer number of options here for M. So this tells us that S minus S must be, well, actually a natural number. Okay, so this tells us that 2S is a natural number, which means that S is of the form, give me another number, L over 2, where L is a natural number. Okay. So examples. If S is 1/2, then M can be minus 1/2, 1/2, right? If S is 1, then M can be minus 1, 0, 1. If S is 3.5, then M can be minus 3/2, minus 1/2, 1/2, 3/2. Okay, and so on. So this is kind of us limiting the number of steps we can go vertically, up and down. Okay, now a funny thing of characterization, somehow particles that have spin that behaves like this was for the case of the electron, right? There's only two values for the Z component of spin. It was up or down. Particles that behave, that have this, they have a different kind of behavior than particles that have spin like this. So in particular, the ones that have spin integer spin, they're called bosons. So S is a natural number, and fermions are the ones where, sorry, S plus 1/2 is a natural number. Okay. We don't have to worry so much about this distinction for now. If you take quantum mechanics 2, then you look into systems that have fermions and systems that have boson, and see the differences in behavior between them. Okay. You see an example of this with the explicit forms for the operators in the tutorial this week. All right. But we are not done yet. So I said that we would look at this picture and try to bind it vertically, which we did already, and now also kind of horizontally. Okay. So now the Hilbert space horizontally, meaning things that don't change the Eigen state. Okay, so let's take two states. Let's take these two states, M alpha and M beta. So they stay kind of in the same horizontal line, satisfying that they are orthogonal, equal 0. Okay, and now we'll see what happens when we act with the raising operator on them. So let's see what happens. So if you have M alpha, M beta, and then you act with the raising operator in both of them, so here you get S plus, S plus, and here S plus dagger, which is S minus, right? And we're going to look at this in a product here. Okay, well, we know what this was. Just before, we saw that this was S squared minus SZ plus H bar. right? It's exactly the same as here, right? This was exactly the same situation, except here we have a beta on one of the sides. So it's the same thing here. Okay, so we just replace it with this thing. So that's going to be M alpha. And now here, what was it? S plus 1 H bar squared minus M plus 1 H bar squared M beta. Okay. Okay, so this is just a number. So then we have the number times the inner product. Okay, and this was 0 by hypothesis. So what does this tell us? It tells us the following, that if I have two states that are orthogonal, when I raise them both using the S operator, they should still stay orthogonal. Okay. So here's the SZ, and here's the alpha. Oh. So if I start with, I don't know, M equals 1, and I have these two states here, then at the end, they should be mapped to different states by this S plus operator. Okay. That still stay orthogonal. Which means that the dimension of this Hilbert space should be as large, at least as large as the dimension of this Hilbert space, right? Because there must be space here for these two to still be orthogonal. Okay. So if I take all of these states and defines a basis and also normal basis here, and then I map each of them up, I should still end up with at least an orthogonal basis. Okay. So this of course, the exception to this is when M equals S, right? When I'm already at the very top. If M equals S here, and then I apply this S plus operator, then what I'll get is just this term equals this term, so I get 0, right? So it goes all the same, say dimension 3, dimension 3, dimension 3, and then suddenly 0. Okay. But until then, they must all have the same dimension. Well, at least the same dimension. It could still be the case that I start with 2, and then here there's room for 1 more, and here there's room for 2 more, for example. But the conclusion is that the dimension of this space here must be larger than the dimension of M. Okay, for all M smaller than S. But now, the thing is, we can do the same if instead of applying here S plus, we apply S minus, right? We'll do exactly the same, we do the same calculation, there'll just be a minus sign where there's a plus here. And you'll get exactly the same result. So you'll end up that when going down, you also need to have enough room for all these states to stay orthogonal. So when going down, we'll also have that dimension of M minus 1 must be at least as large as dimension of M for all M larger than minus S. Yeah. Okay. So then the conclusion is from this is that dm prime must be the same dimension as dm for Lm between minus S and plus S. So what we saw was that we cannot have this picture of having states of different dimensions for each of these subspace, but they all must have the same number of orthogonal states. So what's the conclusion? Is that our picture looks more like this, M alpha, M alpha prime, M plus 1, M plus 2 alpha prime. But we still don't know if these operators map things like this or like that. We don't know. But we know that they must always be the same number of states for each M. Okay. And it goes up to minus S. Right. So that's M and that's kind of alpha. Good. And what this tells us is that we can take this Hilbert space, which we called HS, and just take it as a tensor product of two Hilbert spaces. So the spin or the spin Z and this extra degree of freedom, that's the alpha. Okay. So what this tells us is that we take this, okay, this, if you want to be precise, is an isomorphism. So if you take this state M alpha, we can call it spin as a tensor product of the spin and the alpha in this extra space. Yeah. Now this is very remarkable. Remember, we started only with the commutation relations between these operators. We don't know what they look like at all. And we already found out that, well, this Hilbert space must be, so this has dimension. What's the dimension of this is 2s. Sorry, is s plus 1. Is that true? Yeah, that's right. Yes. And the dimension of this is this mysterious dm, right? Good. Good. So we start only with the commutation relations, and you already found out a lot about how these operators behave, what the Hilbert space looks like. We know that we can always, whatever Hilbert space it is, we can always split it into the spin component and something else. Good. And we know that the spin component is limited by this M belonging between minus S and S. And the extra could be anything, but we know it must be kind of independent. Good. So now we will look at some examples. So I think maybe in the next lecture, we'll see some examples where this alpha becomes another spin system. So for example, it could have two qubits or two electrons, each of them with a spin up or down, and you bring them together, and then you have two kind of spin systems. But that's maybe too much for now. So let's consider cases where this Hilbert space is trivial. So there's only one value of alpha, okay? So all you have is the spin direction. So those are called simple spin systems. And that's when the dm equals 1. Okay. So this h extra is trivial, meaning it's just a number, right? It's just C. Okay. Good. So then our state can be labeled just as M. Okay. And let's start. And now we can find the exact form for each of the states. So remember that we knew this, but we don't know what this normalization constant is here. Okay, so we want to find an exact form for what this M plus 1 is. Okay, so let's say that state minus S, we fix it. Okay, And then we say that, well, let's see, m plus 1, we're going to call it just, well, s plus acting on m times this constant. And this constant should lead to normalization, right? And it's very simple. So if you look here, right, we have this s plus acting here and x plus acting there. So we want this whole thing to be 1, okay? And this whole thing gives us this thing here, essentially. So let me do it again. So we want s plus m, m, s minus. This was equal to h bar square s plus 1 minus m plus 1 times m, right? So if you want this to be normalized, then you have to have here 1 over square root of this thing, essentially. So we have here square root of s plus 1 minus m minus 1. This is just what we used to go in there. Okay, so this tells us what? This tells that when you have s plus acting on a state m, what you get is m minus 1 times the opposite of this, m plus 1 times the inverse of this constant, s plus 1 minus plus 1. Okay. Which means that we can represent s plus as the sum over m of this thing here. We just expand this matrix in this basis and we get what? We just get this. Okay. And of course that when m equals 1, then this whole thing gets 0, so it's not a problem. So when we reach the top, it ends. So, okay. So the way this Hilbert space looks is kind of like this, where this is m equals s, m equals minus s, and that's it. So the s plus take you up times the constant, and the s minus take you down. And if you apply again on top or the bottom, you get 0. Good. So this is exactly like this energy battery that we saw before. And in fact, the energy battery can be modeled by one of these things exactly. And these operators look a lot like this operators that ended in the thermal engines, right? That would raise or lower the weight in the battery, the energy of the battery. Okay. Good. You can do the same for S minus. So you can also write S minus is going to be the sum over M H bar. And I think the only difference that here is going to be M minus 1. Yeah. Okay. Good. So now the only thing missing is try to see now what happens when you have two single spin systems. And then in the next class, we talk about this orbital angular momentum as well. Okay. We'll start now and we'll see how much you can do now. So now let's suppose that we have a Hilbert space that's composed of H of spin 1, H of spin 2. Okay. And they could have different numbers S. So it could be H of S equals 1/2, like we saw before, times S of equals 1, for example, right? Where here you have dimension 2 and here you have dimension 3. And what we want to do is we want to see if there's like a global spin operator for this composed thing. So this is an example. And in fact, there is. So if we define Sx to be Sx1 tensor Sx on the tensor identity in the second system plus plus nothing on the first, and this in the second system, and similarly for xy and for xz. Y2 okay. Then it will turn out that they satisfy the same angular, the same commutation relations. So for example, we can do this here. What is this? Oh, that's not what I meant. Oh, honestly, okay, give up. So we have Sx1 identity in the second plus Sx2 times xy1 identity in the second plus 1 sy2 minus the other way around. So sy1 identity in the second plus identity in the first sy2 times sx1 okay. So if you look at this, so let's see what terms we have here. In fact, that's not the nicest way to do it. That's not the nicest way the easiest way to do it. Let's do it in a nicer way. So we have the commutator between two operators, and now this copy function will work. You'll see. Copy, paste, very good. Yeah, this is the nicest way to do it. Here we have the y's. Okay, so we have 4 terms. So we have SX1 identity, comma, Y1 identity plus SX1 identity times identity SY2 plus 1 tensor SX2 times Y1 identity in the second. At this time, it's not fun math, it's just slope math. SX2, and here we have identity in the first and XY2. But remember that operators that act on different systems commute, right? So here we have SX1 in the first and XX2 in the second, so they will commute because they don't act on the same system. So this is 0. Similarly here, so you only have these two terms surviving. And you know what this is? So the first term is just SX1 SY1 times identity in the second system. But that's what? This is just IH bar SX1, okay, plus the other one, which is going to be identity in the first system, times SZ on the second system, IH bar. But that's just IH bar, our newly defined SZ, so this SZ here, this one, right? Okay, so what we get is exactly the same commutation relation. So we can, for a moment, forget that they come from, we can forget what these operators are about. We can forget that they came from these individual systems that we put together. All we have is these commutation relations. Okay, we have this for these two and the same for the others. And now it means that we can apply the same analysis as before, and we say, well, then we have spin again. So this again defines spin. And now what is left to decide is like, what's the value for S, right, of our spin? And so what's the dimension of this Hilbert space and so on. And it's going to turn out to be a bit more complex than you could think originally. So there'll be several values for S. So we'll be able to think of the total Hilbert space. So which, remember, it started as this spin 1 tensor spin 2. We're going to see it as a sum of the, sorry, this is a direct sum of HS for some S that comes from there. So we'll get Hilbert spaces for different values of the eigenvalue of S squared. There'll be several options, and each of these options will lead us to one of these Hilbert spaces with value S. So we'll get kind of, for example, this plus this. Okay. We will see an example of this. So let's take the simplest example so that we can see what these are, what this looks like. So we take S1 to be the same as S2 to be 1/2. Okay. So we have essentially 2 qubits. And in order not to confuse things a lot, we're going to label the SZ1, the Hilbert spaces as, sorry, we're going to label the states on each space, the M, with like an arrow up if it's positive and an arrow down if it's negative. This is very common in physics. Half of the time you see, instead of zeros and ones, you just see an arrow up and an arrow down. Okay, so the idea being that SS1 applied on this on the first system, this is plus h bar over 2, and that as that 1 took 2 equals minus h bar over 2. Okay. So the Hilbert space H, it's kind of a span. It's 2 qubits, and just like before, we could have state 0, 0, 0, 1, 1, 0, 1, 1. It's exactly the same, so it could be up, 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 down, down, up, down, down. Okay. And this is system 1 and system 2. Okay. All right, so now we're going to see how these operators, the global operators that we just defined, act here. Okay, so let's see. Well, what's SZ acting on up, up? Well, that's SZ1 times the identity plus, plus the identity times SZ, first system, second system, acting on plus, plus. Well, the first one just gives eigenvalue plus h bar over 2 and does nothing, and the second one gives plus h bar over 2, right? So up, up. Okay. So that's h bar over 2. Which means that we can, up, up, which means that we call this stage, well, this stage corresponds to having S equal 1/2 and M equals 1/2. So we can call this stage up, up. We can call it the state 1/2, 1/2. Okay, where this one is S, and this one corresponds to M. We're going to do the same for the other cases, for these other states here. And yeah, we will see what happens. But I have to stop here, so we'll continue this in the next lecture.